So in the last lecture, we started a discussion of the Schwarzschild solution. So you remember that the Schwarzschild solution is supposed to be a solution of the field equations where you assume that the metric is both static, which means there's no time dependence, and isotropic, which means it depends only on functions of R. And one can show, in fact, that any general static isotropic metric can be reduced to this form by suitable redefinition of coordinates, times, and so forth. So this is the starting point, right? And we discussed in the last lecture how you can then, by a little bit of work, derive all the quantities that you need for the field equation, so you can calculate the affine connection first, right? And then from the affine connection, you can get the components of the Riemann tensor, the Ricci tensor, and the scalar curvature. Now, because of the symmetry of the metric, there's a lot of these components that vanish. So you have the only non-vanishing components of the affine connections are the one that I wrote down on the blackboard, right? And so everything else is zero, or it can be found by symmetry, because remember, the affine connection is symmetric in the two lower indices, right? So from this, it is fairly straightforward then to calculate the Riemann tensor, and in particular the Ricci tensor, which is the one that enters the field equations. So I'm going to write that out here so we can stare at it for a little bit. And so we have four field equations, right, corresponding to the TT, RR, theta, theta, and phi, phi components of the Ricci tensor. So RTT is equal to minus B double prime divided by 2A plus 1/4 times B prime over A times A prime over A plus B prime over B, where the prime, of course, is the derivative with respect to R, because that's the only variable that's of interest in this problem. And then minus 1 over R times B prime over A. And so that's the first equation. Then the first equation being RTT is going to be equal to 0, right? Remember that we are looking for solutions that satisfy R mu nu is equal to 0, because that's all that's left of the field equations if we are looking at, no sources anywhere except possibly at the origin, right? So, and the cosmological constant, of course, is also 0, right? So we don't have that term either. So RR is equal to B double prime divided by 2B plus 1/4 times B prime over B times, again, A prime over A plus B prime over B minus 1 over R, A prime over A, right? And then we have R theta theta, which is equal to minus 1 plus R divided by 2A, R divided by 2A, times minus A prime over A plus B prime over B plus 1 over A, and R phi phi, which is equal to sine squared theta times R theta theta, right? So these are the four equations that we want to solve, those four expressions all being individually equal to 0. Now, we notice, first of all, that because of the symmetry of the problem, we don't even need to look at the phi phi equation, because as soon as R theta theta is 0, R phi phi will be 0 as well, right? Also, these three equations are not independent, because we discussed right, at length the fact that the field equations themselves are not independent because they're coupled through the Bianchi identity, right? So presumably what we have to do is just solve two of them and we'll be done. We have two unknowns, which are the A and the B functions. And when you stare at this a little bit, and we kind of discussed it briefly at the end of the last lecture, you find a solution by fiddling around with these equations and looking for what kind of expressions will satisfy them. But in fact, what happens in this case is that it's enough to have this expression to be equal to 0. A prime over A plus B prime over B is equal to 0. And then the remainder also has to be 0, which means that B double prime divided by 2A with a minus sign minus this piece here is also 0. And that actually works. So you can then see that the other equations are satisfied as well. So the solution is that the first thing we look at is RTT is equal to 0, right? And as I said, we can break this down into A prime plus over A plus B prime over B is equal to 0. And 1 over R times B double prime plus, 1/2 B double prime plus 1 over R B prime is equal to 0. This will actually work to break those down in this way. And if that is indeed the case, then the solution to this is that B of R is going to be given in terms of some integration constant. So C1 plus C2 divided by R, right? But now the thing is that B of R, again, now we look at the weak field limit and try to recover the Newtonian result for this. And so B of R is equal to minus G naught naught, right, which is equal to 1 plus 2 phi, right? So that means that in order to get the 1, we have to have the C1 is equal to 1, and the C2 has to be equal to 2 mg. So this is equal to 1 minus 2 mg divided by R, right? And so that is the first piece, right? And now we can look at, so this would be equation 1, right? And this would be equation 2. And so equation 2, we can solve it because now we know what B is, right? So from that, we find that B, again, is, at A, right, at A is just given by A of R is given by some other constant, which you can call C3, divided by 1 minus 2 mg over R. And C3 is determined by the fact that when we go sufficiently far away from the source, we should just recover flat space-time, right? So if you look at the metric, when you go far away, then you should just have the flat metric. So A and B should become 1, right? So as R goes to infinity, A of R should go to 1, and that tells us that C3 is 1. Okay, so we put that in here, right, 1, and that's the second piece of the solution, right? So we have everything that we need, right? We have determined that the solution is given by those expressions, and that A of R and B of R both, as R goes to infinity, go to unity, which is that they get back the flat metric. And so now let's think about this a little bit, right? Because certainly it is a very interesting result. I think you appreciate probably by now the fact that the field equations are highly non-trivial. They're very complicated. They involve, this inverse of the metric, determinant of the metric, which enters the inverse, and so forth. So it's a real mess. So the fact that you can find an exact solution is remarkable, right? No approximation whatsoever has been done here, right? You find an exact solution. And it's one of those rare cases where you do, because you can imagine that in general, finding exact solutions to the field equation is not easy, right? The other thing is that the solution is singular, right? The solution, if you look at these expressions, seems to, the B of R, right, seems to vanish at, right, so B of R at R naught or Rs equal to 2 mg, right? So there is a point in R where something happens, which is this horizon, right? not only does B vanish, which means that the relationship between the proper time and the actual time involves a factor of 0, right? There's a coefficient which vanishes at that point, but also the other component of the metric blows up, right, on this horizon. So, of course, this is something that one needs to worry about, because in particular, if you look at the form of the metric, which I'm going to rewrite here on top of the blackboard, you notice that the sign of the timepiece actually changes sign when you go through the horizon, right? So if you look at the proper time interval, d tau squared, right, that involves b of r times dt squared minus a of r times dr squared minus r squared times the solid angle, right? So when this object changes sign, we kind of worry about it, right? Because you were supposed to have a positive function multiplying this. So there is an issue of whether actually the region which is inside this Schwarzschild radius or this horizon, whether the region inside is actually represented correctly with this metric, right? Or whether this is just only valid when r is greater than 2mg. So now, you might think that this particular solution might apply to a star. So that is usually not the case, right? Because in the case of a real star, right, if you have a real star of mass m, right, then generally what happens if you go to sufficiently short distances, right, if this is the origin, then if you go to coordinates that are close to the origin, then at that point, of course, this solution will no longer apply, right? The solution will no longer apply because in this region, what will happen is that there's going to be matter, right? There's going to be matter of some sort, right? And so that means that the T mu nu in that region will be non-zero, which means that inside the star, you will actually have to use a different set of equations. You have to solve the equations for a static isotropic metric where you have a T mu nu as a source term in the field equations, right? So nevertheless, we can look at what kind of sizes we get, right, for different mass objects. And so, for example, if you look at right, so if we look at the sun, right, if we look at the sun, then the mass of the sun, of course, is known. Newton's constant is known as well. And so in that case, Rs is about 2.95 kilometers, right? So the radius at which the singularity happens inside the sun is a very small radius. And of course, as I said, in that region, this approximation of just using the T mu nu, taking T mu nu to be 0 is incorrect, right? So when we're dealing with inside the sun, we should include the fact that the density is non-vanishing. Now, nevertheless, we can think of a situation where perhaps you can have a sufficiently massive body that collapses to a size that is comparable to the Schwarzschild radius. And so we can work out what Rs is for different what Rs is for different mass objects, right? And so we found out that, for example, for a proton, right? For a proton, right? For a proton, the Schwarzschild radius is about 10 to the minus 40 centimeters, right? So it is completely irrelevant if you have a particle that is very light in mass, because this radius is, of course, much, much smaller than the size of the proton, right, which is about 10 to the minus 13 centimeters, right? So as far as particle physics, this kind of sizes are kind of irrelevant, but you can have objects that have a Schwarzschild radius which is significant because you have a very large amount of mass in it, right? So if you look at the center of our galaxy, then at the center of our galaxy, one can actually estimate that there is a very massive body. And I'm trying to get here the number for that thing. And I believe it is of the order of a few million solar masses, right? So right, and so in the case of this object, then you have a Schwarzschild radius which is significantly larger than what you would have for a single star. So in fact, you can go at and look at other galaxies. And one notable example is M87, which is nearby fairly because it's in the Virgo cluster. So it's a cluster of galaxies that is fairly close to our own local group. And in that case, you find that in fact the mass of the object that is at the center is much larger than what is at the center of our galaxy, and it is of the order of billions of solar masses. So again, you're dealing with an object that is really quite huge. So it is in fact possible to have black holes in which this or Schwarzschild solution where this Schwarzschild radius is very large. And so the question then arises if this horizon that we look at, if the singularity is in fact physical, right? So first of all, one has to take into account that in general for this astrophysical, and by the way, there's also quasars, which also are supermassive black holes, presumably have supermassive black holes at their center. So the question then comes up, if is the Schwarzschild, right, singularity physical, right? So is the singularity physical, right? Because we do have that some components of the metric go to 0 or go to infinity at the Schwarzschild radius Rs is equal to 2 mg, right? And well, it turns out that to some extent they're unphysical, because one of the things that we learn in general relativity is that the physics is described in different ways by different observers, right? So you can have different coordinate systems, so that one observer describes the physics in his own coordinate system, another one uses a different coordinate system and comes to somewhat different conclusion. They're in fact both physical, right? Because what happens from my point of view is just as physical as what happens from your point of view. Now, the view of general coordinate invariance is, of course, that the laws of physics are going to be the same for those observers, right? They're all going to describe the physics in terms of these basic equations, which is the Einstein field equations, right? But nevertheless, you're going to use different coordinate systems, right? So then the question arises, if you're looking at something like a black hole, right, the solution we have obtained is described by an observer that is located at infinity, basically, right? So he's looking at this object, right, at this Schwarzschild solution from out here, right? He's looking down, and so there is a radial coordinate that connects him to that. And he discovers that as we look at the black hole, things happen when you get close to this horizon. In particular, there is a redshift, right? Because remember from the discussion we had a few weeks ago, right? You have this redshift that is due to the presence of gravitational potential. And that is, of course, the B function here, right? The B function is precisely what is giving you this redshift, right? Which means that if an observer at infinity is looking at a spaceship that is dropping into the black hole, and that if that spaceship is emitting some sort of light signal towards us, we see this effect of the redshift as he plunges into the black hole. And so that's exactly the same as what happens when we looked in the weak field limit at the slowing down of clocks in a gravitational field, right, a few weeks ago. But what is interesting in this case is that the slowing down can become extreme, because the slowing down can be 0, right, or infinite, depending on how you phrase it, right, because of this d tau squared being equal to b of r, which is 1 minus 2mg, times dt squared, right, minus the rest. So you have that this factor that gives you the redshift actually vanishes on the horizon. So you have an infinite redshift at that point, right? So the question is then whether a different observer will observe the same thing, whether the singularity is actually present for all observers, for all different coordinate systems. And the answer is no. The answer is no, because you can construct a different coordinate system, right? Remember, you have infinitely many choices of what coordinates you use in order to describe the physics of this problem. So the statement is that you can actually construct some other coordinate system, which we can call t prime and r prime, right? Which will be just as legitimate as the original one, in the sense that it will satisfy, right, whatever metric you write down, then will satisfy the field equations. But in another coordinate system, you can find that there is no singularity on the horizon, right? So at r equal to mg, nothing happens. So this singularity is something that is specific to some set of coordinate system, including the Schwarzschild one. And that what I just described actually happens was shown very explicitly. Well, originally by actually Pain-Levé, because there is a coordinate system named after a French mathematician by the name of Pain-Levé, which we'll discuss later on. In 1921, he wrote down a set of coordinates for this. Again, for the static isotropic case, we don't have this horizon singularity, right? But another way of looking at this is through what are called Kruskal coordinates. Right? So Kruskal coordinates is a new set of coordinates, right? So we start out in the Schwarzschild case. Of course, we have r, and we have r, t, and then theta and phi, right? And now we can look at some other coordinate system, and the Kruskal coordinates. We don't want to use r prime and t prime, because otherwise it's going to get a little bit cluttered. So they're called u and v, and then we still have the angles, which are theta and phi. So the coordinate change only involves the time and space coordinates. And the way he defined it was in the following way, that u squared minus v squared is through some sort of implicit relationship. U squared minus v squared is equal to some constant, which we take to be 1, times r divided by 2mg minus 1 times e to the r over 2mg. And we need, of course, a second relationship, which is 2 times uv is equal to u squared plus v squared. 2v divided by u squared plus v squared is equal to the tanh of t over 2mg. Okay. So this is a coordinate change from one to the other. And one can write d tau squared in this coordinate system, which I won't do. And of course, it's relatively easy to do in principle, because you just write the Schwarzschild metric, right, which contains a and b, and then you do this replacement wherein the r becomes some function of u and b, and the t becomes some function of u and b, which is given by these two relationships, right? So what one finds, and there is a very nice discussion of this in Jim Hartle's book, is that you can actually solve explicitly for u and v, except you get different solutions depending on whether you're inside or outside the horizon. So if you are inside, if you're outside, sorry, so if r is greater than 2mg, then the solution is that u is equal to the square root of r divided by 2mg minus 1 times e to the r over 4mg times the cosh times the cosh of t over 4mg. Right? And so that's explicitly u in terms of the original coordinates r and t. And v has a rather similar expression, so it's the same square root, the same exponential, and the sinh, right, of the same thing. And if you are for r greater than 2mg, so inside the horizon, then the solution is fairly simple, but there is a change of sign inside the square root. And so u is equal to the square root of 1 minus r divided by 2mg. So you notice that there has been a sign change in the argument to the square root, and then the rest is pretty much the same. So e to the dot 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 times the cosh. The first one becomes a sinh, and the v is the same square root times the same exponential times the cosh of the same argument that we had up there, right? And you can actually verify that if you plug those in, if you take the square of the first one, subtract the second one, then the relationship is correct. And then you can do all sorts of mappings between one coordinate system and the other. So for example, you can look at light rays. What does a light ray look like in one coordinate system, and what does it look in the other one? And so for example, you can start looking at r equals 0, and r equals 0 it becomes, right, which is the origin in the original Schwarzschild coordinate. In this case here it becomes a parabola, right, because the origin is mapped into v is equal to the square root of 1 plus u squared, which is a parabola. And the lines of constant t in the original Schwarzschild coordinates become, well, something that looks slightly different. Becomes tanh of t divided by 4mg is equal to v over u if r is greater than 2mg, and if r is less than 2mg, then it's the tanh of t divided by 4mg, which is not equal to v over u, but u over v, so just the inverse of that. Right? So you can work out a few things, and you can, you notice, for example, then when t goes to plus infinity, then u becomes the same as v, and when t goes to minus infinity, u becomes minus v, right, etc. So you can map one coordinate system into the other. Now, perhaps the most important aspect of this is that even though the original metric was singular at the horizon, the new metric is not. So in the new metric, everything is well behaved. And in fact, these functions connect nicely between the two regions, right? And so the singularity at Rs equal to mg has disappeared. Right? So the singularity is gone. Right? So that seems to indicate that the singularity that we saw in the Schwarzschild solution was somehow an artifact of the particular coordinates that we're using. Now, I said before, though, that different coordinate systems nevertheless do represent different observers, right? And so we should still say that those observers are physical, right? Because if such a coordinate system exists, then it describes the physics from the viewpoint of that particular observer, right? Nevertheless, what we have noticed here is that even though it is very much physical for that particular guy that describes the physics in terms of the Schwarzschild coordinates, you can find other coordinate systems where there is no singularity on the horizon, right? So it is a matter of perspective, right? And so what do these other coordinate systems look like? Well, generally, they just correspond to an object, right? We'll see also this in the case of the Pan-Levé coordinates, right, which sometimes are referred to as the raindrop coordinates, because you can find coordinate systems that are attached to a spacecraft that falls into the black hole. Right? So if you do fall into the black hole, then the description is quite different from the Schwarzschild observer that is located at infinity. So you have these two representative coordinate systems, right? One is the guy that is sitting at infinity and is observing this object, right, which is far away. And the other reference frame is attached to a spacecraft that is plunging into the black hole, right? So as the spacecraft is plunging into the black hole, you have this redshift effect. So if he's trying, right, if the spacecraft is going in, right, it is sending a light signal to communicate back with the observer at infinity, but that light signal will be redshifted, right? And in fact, we know that the redshift becomes infinite at this point, right? So when it crosses the horizon, because of the function b, the relationship between the proper time and the coordinate time for the Schwarzschild observer, the redshift becomes infinite. And so what the observer at infinity sees is the spacecraft going in, the light getting increasingly redshifted, and then at some point don't see anything anymore. And the point at which you don't see anything more, because the redshift is infinite, is where the spacecraft crosses the horizon, enters into this new region, right? And once it enters in that new region, whatever light he emits gets basically sucked in back into the interior part of the Schwarzschild solution. And so communication is lost, right? Nevertheless, nothing really dramatic happens to the spacecraft, right? So the spacecraft, as it crosses to the horizon, is pretty much unscathed, right? It goes through and everything is fine. I mean, we don't want to say the same thing, of course, for a real black hole, because there's going to be intense tidal forces, which at some point will rip the spacecraft apart. But apart from that particular scenario, as the spacecraft goes through the horizon, nothing dramatic happens. And so that explains the fact that different observers come up with quite different descriptions of what happens in that region. In fact, one can verify, right? We do know that a way to describe events that are going to be the same for different observers is through curvature invariance. So for example, you could calculate Riemann squared on the horizon. You find that Riemann squared on the horizon is finite. There is no singularity in any of the curvature invariants on the horizon itself. The singularity is a coordinate singularity. Right? So there's a difference between singularities that are invariant, which means they're detected by any observer in any coordinate system. And here, of course, we have one of those invariant singularities. That's r equals 0. Because no matter what observer you are, you will find that there is, in fact, a singularity in any invariant at r equals 0, because we have a point source at the origin, right? So that's not going to go away. But the singularity on the horizon, that is something that is coordinate dependent. It's coordinate dependent. So this set of coordinates that Kruskal wrote down completely eliminate that singularity on the horizon at r equal 2mg, right? So now Kruskal came up with a nice way of indicating what is going on through a diagram. So this is called the Kruskal diagram. So in a Kruskal diagram, you draw things in terms of this coordinate that he talks about, right? And so one coordinate is the vertical one is going to be the v, and then we have the horizontal one, which is the u, right? And so now we can map, based on what we discussed a moment ago, we can map what happens for one observer into what happens in these Kruskal coordinate systems, right? And so the first thing we're going to draw is the line that corresponds to r equals 0, right, in the original Schwarzschild coordinates. So that is equal to r equals 0. And in fact, anything that is less than r equals 0 is meaningless. So the physically allowed region is outside of that excluded one. And there is an equally excluded region out on this side. Actually, these are 45 degrees. So let me draw that like this. Right? And so there is another excluded region out here. And now we look at an observer that is falling into this black hole, right? Falling into the black hole means that eventually, so it's a radial plunge. So in other words, it's just going straight into the thing, right? And eventually he's going to reach r equal to 0, right? So we are looking at a trajectory where he goes like this down, right? And he could be free falling, or he could be, braking. I mean, the spacecraft could do all sorts of different things. And the simplest case, of course, would be the free falling observer. And in this coordinate system, we do have light rays that can be emitted. And so light rays correspond to cones, right? Because, so we draw a little light cone here. Light cone, right? So that means that a light ray, and they're supposed to be at 45 degrees again, so let me try to represent that. So we are going to draw a few of these, right? And so as he goes in, he's going to emit some light signal, and the light signal would come out in the direction of this light cone like this, right? And as he plunges into the black hole, for a while there is no problem. In other words, this light signal will reach infinity. But out here there is a line which I'm going to draw with the colored pen, which corresponds to the horizon. So the horizon in this coordinates, in the Kruskal coordinate system, is so it's going to be a line that looks like this. Right, so this is r equal to mg in the original Schwarzschild coordinate system. Is now a line at 45 degrees. And the other thing I want to draw here is, remember that when you have an observer that is at fixed time in the original coordinate system, that is a parabola. So we're going to draw this as corresponding to the observer at some fixed large r, right? So he sits out here. And so at some point he's going to receive a light signal. And that will happen, though, provided that he does not emit light once he is inside the horizon. So when he is inside the horizon, he's going to have light cones with directions corresponding to the emitted light, which is still at 45 degrees. But now what happens is that the light is going to go here and at some point hit r equal to 0. Right? So something dramatic happens. This curve here eventually gets infinitely close to the line r equal to mg. So once he's past the horizon, the light does not have a chance to escape. And so it's really a matter of perspective, as I said, right? Depending on what coordinate system you're in, you perceive that certain things happen that are rather strange or not, right? For the observer that falls into the black hole, things are fairly normal and well behaved until, of course, he hits the origin, right? By the time he hits the origin, the gravitational forces are strong enough to just completely rip him apart, right? So now the idea that you could have something like this, right? So the term black hole was invented by Wheeler around 1968, right? So this Schwarzschild solution existed for a long time, right? Because Schwarzschild derived it in 1916, which is just about the same year as the theory of general relativity was written down. And so it sat around for a long time, and people thought it was maybe some sort of mathematical oddity, right? That, in fact, if you're looking at real stars, you would not have that kind of singularity because the T mu nu would be non-zero inside the star, right? But and then Wheeler in 1968 gave it a name. He thought that objects like this actually would be plentiful, right? We know now that most galaxies will in fact have a very supermassive object at the origin, right? Because what astronomers do nowadays, of course, is they look at the velocity distribution as a function of radial distance. And that velocity distribution tells you something about the mass that is enclosed within a region of radius r, right? And the velocity distribution is something that looks like this, right? And then the signature for a black hole is that the velocity distribution for stars in a galaxy is such that it has some sort of cusp close to the origin, right? So the velocity increases dramatically. And from the behavior of this curve, from the behavior of velocities of the stars close to the center of the galaxy, you can infer if you do have a black hole or not and what kind of mass it has. And the conclusion nowadays is, of course, that most galaxies do have a supermassive black hole at the center. And so that means that, well, how many galaxies do we have in the universe? Well, one thinks that there are trillions of them, right? So we have trillions of objects that are very massive and sit at the center of these various galaxies. So there's plenty of them around. But the idea, so after Wheeler proposed the name, this became an intense subject of research in the 70s and 80s. And today we know that there are many of these objects around. Nevertheless, people already in the 19th century considered the possibility that you might have an object that is of this type. Incidentally, Feynman does not use the name black hole for it. He calls it a wormhole, right? So when Feynman wrote his book, which was in the early 60s, the term black hole had not been invented yet. So he refers to it by a slightly different name. And so nevertheless, this idea that you could have an object that was massive enough that it would trap anything was already proposed by Laplace at the beginning of the 19th century. And so classical black hole, right, is something that you can consider because you consider an object that is very massive, right? And then you write down basically Newton's equation or conservation of energy, right? So 1/2 mv squared minus m times capital M times g divided by r is equal to the total energy, right? And so now you want to consider a situation where the energy is zero because you look at a situation where the particle escapes at infinity with the velocity which is zero. So at infinity, the velocity is zero, right? V equals 0 at infinity, and then the potential also is 0, right? And so that gives you the escape velocity because you just have 1/2 mv squared is equal, you can cross out the mass, is equal to little m times big M times g divided by r. You can cross the mass of the particle itself out, and so the object you're dealing here with is the object like the sun that has a mass which is capital M. So as a result, you have that v squared is equal to the square root of 2mg over r. V is equal to the square root of 2mg divided by r, right? And so this would be the escape velocity. At some distance r, right? So you can work that out for the Earth, and for the Earth it's whatever 47 Mach or something like that. So 34, Mach 34. And so what happens if the object that is trying to escape is light, right? So for light, for light, V is equal to C, right? And so you have that C squared is equal to 2mg over r, right? And so you find that the r is in fact this rs, right, is equal to 2mg, right? So you determine that if the speed of the object that is trying to escape, then if you are at this radius or a radius that is less than that, then the light will not escape, right? So this is already the kind of argument that you can construct out in classical mechanics for an object that gets trapped by a gravitational field that is sufficiently strong, including a photon, right, a beam of light. Well, this is of course interesting, but it is complete rubbish, right? This argument is complete nonsense as it stands, and the reason why it is complete nonsense is because you cannot use 1/2 mv squared as the kinetic energy for a photon, right? So the fact that you in fact do get the Schwarzschild radius in this case, right, that you get a relationship which is just like the one that you get for the relativistic solution of the field equation, is pure coincidence, right? So this argument is nonsense. And as it stands, right, because of using this for light is meaningless, right? So in fact, you do have to have a relativistic treatment, and what we have done is correct. But nevertheless, that did not prevent people to at least think about this problem already before general relativity. They thought of the possibility that you could have an object that was massive enough that whatever would be emitted from that object somehow would be trapped and sucked back into it. And so the notion that you could have these supermassive objects predates actually general relativity by quite a bit, but it has become particularly, I think, interesting in recent years. So now we want to kind of move on, right? And one of the things we want to look at is use the fact that we have developed, right? We have developed, obtained an exact form for the solution to the field equations, right? Based on the static isotropic metric. And so we do know what the metric looks like if you have a very massive compact object of mass m, right, which is described, for which the metric is described by this B of r, which is 1 minus 2 mg over r, and A of r, which is b to the minus 1 of r, right? And this will apply as long as this object is very compact and very small, so that it's essentially just some sort of point source at the origin. And that idealization is actually pretty good for discussing a number of things that are of interest in general relativity, including the motion of the planets, and in particular the precession of the perihelion of Mercury, as well as other effects that you can have in the solar system, such as radar echo delay. Right? For most purposes, the sun can be just shrunk to a point with a mass m, right? I mean, there has been a long-standing debate, I think it was started by Dickey in the early 60s, of whether some of the relativistic effects could be due to the oblateness of the sun, right? Because the sun is in fact not a perfect spherical body, right? There is some deviation from perfect sphericity. And what Dickey, of course, at some point, I shouldn't say claimed, but at least brought up, was the possibility that some of the effects in the precession of perihelion of Mercury could be due to the sun's oblateness, that there could be some additional perturbation. And that turned out to be not true, because the oblateness is there, but it's not large enough to give a significant contribution to the precession of the perihelion of Mercury. So for our purposes, a lot of these solar experiments and solar tests for GR can be treated by just having the Schwarzschild solution, which assumes that you have a point, right? And so that's something that is, of course, easy enough then to work out. That is, we now know what the metric is, right? So we have all the components of the metric. We have solved the field equations, right, which are essentially are mu equal to 0 outside the source that is at the origin. And so the next step is to figure out what a planet will do, for example, right, or light, right? Deflection of light by the sun is also important, right? But let's first just think of a body of some mass m, right, that orbits around the sun. And so in order to do that, we have to write down F equal ma, right? We have to write F equal ma, where F is the gravitational force. And of course, F equal ma as such does not exist in general relativity anymore because it is replaced by a different equation, which is the equation for free fall, right? So we have to write out the equation for free fall. And so the equation for free fall is that the second derivative of x lambda with respect to tau squared plus gamma lambda mu nu dx mu by d tau dx nu by d tau is equal to 0, right? And that is going to give us the equations of motion, right? So here we're dealing obviously with 4 equations, right? Lambda is equal to, well, in our case, we are going to use the Schwarzschild coordinate system, right? So in our case, we can think of lambda as being 1, 2, 3, and naught, but it is better to just think of it as t, r, theta, and phi, right? And nevertheless, we do have 4 equations, right? And so again, I think it's worthwhile to look at what those equations look like. And we calculated this. We computed the components of the affine connection, and I wrote them on the blackboard at the beginning of this lecture. So we can just read those off and do the appropriate sum, right? You see that there is a summation here. So you have to see what survives and what doesn't, right? And so we do have 4 equations, and the 4 equations I think for completeness, let me just write them out here. And so the first equation is the one for r. So second derivative of r with respect to tau squared. You see that what appears here is always the proper time, so we have that. And plus, and now we got to look up all the coefficients of the affine connection that are non-zero and write those corresponding dx mu by d tau terms. So a prime over 2a times dr by d tau squared minus r over a d theta by d tau, again squared, minus r times the sine squared of theta times divided by a times d phi by d tau, again squared, plus b prime over 2a times dt by d tau squared, and this is equal to 0. So that's the r equation. That's the r equation, right? In principle, of course, there's a lot of terms because of the summation of the mu and nu indices, but because of the symmetry of the Schwarzschild metric, we do have only that a certain number of terms survive. In particular, these are all diagonal terms. You see, they're all first derivative squared of something and no cross terms, right? So that's the first equation. Then we have the theta equation. So second derivative of phi with respect to tau plus 2 over r d theta by d tau dr by d tau minus sine theta cos theta d phi by d tau, and then squared is equal to 0. So this is the theta equation. Then second derivative of phi, sorry, this is supposed to be theta, sorry. Second derivative of phi with respect to tau squared plus 2 over r d phi by d tau dr by d tau plus 2 cotangent of theta times d phi by d tau and d theta by d tau, and that is equal to 0, right? And so that's the phi equation. And of course, we have also the fourth one, which corresponds to the time, right? And that's an essential one too. And so that says that the derivative, the second derivative of t with respect to tau plus b prime over b times dt by d tau and dr by d tau is equal to 0. Right? And of course, everywhere we have this, right, that b is equal to 1 minus 2mg 2mg divided by r, and that a is equal to b to the minus 1. And of course, this at first looks like a mess, right, because we have 4 equations that are rather complicated, and it could take us a while to sort this out. But it turns out that, in fact, even in classical mechanics, you do have several equations, because you have equations for r, theta, and phi, right? So the kind of new ingredient here is that you're writing everything in terms of the proper time. And the last equation is going to be the one that will allow us to replace the proper time that appears in previous equation by the actual time, the coordinate time, right? So this last one is, and in fact, it will be easy to solve it, right? Because the structure is fairly simple, right? And so now it looks like the task might be more complicated than what it is, because in fact, we can see immediately that some of these equations can be integrated, leading to a number of constants of the motion. Right? And those, of course, have to do with the conservation of angular momentum in this case. So constants of the motion, right? We do have that from the theta equation, from the phi equation. We can write this as a derivative with respect to tau of something is equal to 0. And that something is the log of d phi by d tau plus the log of r squared, and this is equal to 0. Remember, we're using explicit form for for a and b, and the other thing is that we're using theta. We're setting theta to be pi over 2, so we're looking at a fixed angle, right? And so that implies that the cos theta, we've made the choice that cos theta is equal to 0, and that d theta by d tau is also equal to 0. So that leads to this equation here. And the t equation also can be written as d by d tau of something is equal to 0, and that d by d tau of something is d by d tau times the log of dt by d tau plus the log of b. The b function is equal to 0, right? So one can simplify things significantly, and another constant of the motion is the total angular momentum, which is r squared d phi by d tau, which we are going to call j, and set that to be a constant. Right? So introduce a constant, which is this quantity here. And so as a result of that, we're just left with one equation, which, if you want, is the top one, right? So we basically don't need to care much about this because of the conservation of angular momentum and introduction of j. We don't need to deal with those two, right? The last equation is the one I've rewritten there at the bottom, which is going to allow us to trade the proper time for the time t. And so that will come at the end. And so using, right, so we have here the angle. We made a choice that the angle is equal to pi over 2. So we can just rewrite this as in the following form, as the second derivative of r with respect to tau squared plus a prime over a times dr by d tau, which is these first two terms, squared, minus the angular momentum, so minus j squared over r squared, actually is r cubed a, plus b prime over 2ab squared is equal to 0. So that's what's left. And this can be written again as d by d tau of something is equal to 0. So we can factor out a d by dt. And so that basically means going from the equation of motion, right? This is the analog of F equal ma, from the equation of motion to an energy, right? The expression for the total energy, right? Which is a constant of the motion. First integral. So dot, 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 right? Dot, dot, dot. And so the dot, dot, dot is this. The dot, dot, dot is a times dr by d tau squared plus j squared over r squared minus 1 over b is equal to, well, when we integrate this equation, we get an integration constant, right? So we can add always a constant to this expression, and that constant, we're going to call it minus e, and is a constant. Right? So now we start to recognize this as the expression for the energy in classical mechanics, right? Because we have the r dot squared, which is the kinetic piece, right? So we have the kinetic energy, and then we have the potential energy. Now I could say that this is the potential energy, but actually not quite true, because we have here in front the A, right, which remember is a function of R, right? Remember that A of R is equal to 1 over 1 minus 2 mg over R. So that goes in there. And the B is 1 minus 2 mg over R as well, right? So this is the kinetic term, but of course we should probably take out that A and bring it over on this side, right? And so we can do that because we can rewrite this. We can rewrite as dr by d tau squared, right? Now usually the kinetic energy term has a 1/2. And of course this is for a given mass, little m, right, which you can always add, but here we don't have that little mass, so we just have the 1/2, right? And so this is the kinetic energy term. If you want in the canonical form, right, where you have q dot squared, or 1/2 q dot squared. And well, then we have the rest, and the rest is of course multiplying this piece here by 1 over a. And so we're going to write that as v effective of r, and then the whole thing is going to be set to 0, right? Or to some other constant, but it will be easiest just to take that constant to be 0. Constant to be 0. And so one can work out what the v effective is, right? Because this v effective, unless we've done some major mistake along the way, this should be minus mg over r, part of it, right, plus some other things, right? And so the v effective is, in our case, is 1 over 2a times j squared over r squared minus 1 over b, which is those terms we had up here, and that's it, plus e, which is equal to 0. And so you can work what this is, work it out, right? And so let me multiply that out. I'm kind of running out of space. And so it is equal to minus mg over r, first of all, and that's the standard Newtonian part. Right. The Newtonian piece should be there, right, somewhere, because this is supposed to give back the Newtonian result for the potential energy right? And then there is a second piece, which is j squared over 2r squared, right? Which is essentially this piece here we divided by 2. And that, of course, we recognize 2 because that's the centrifugal barrier term. Right? Centrifugal barrier term. And we have that in classical mechanics when we do the Kepler problem, right? In 3 dimensions, you get a centrifugal barrier term when you look at the radial coordinate, right? In fact, you have it also in the Schrödinger equation, right? And, well, there is an extra piece, and it turns out that that's all there is to it in this case, that you do have a third piece, which is minus j squared times g times m divided by r cubed. And this piece is new. This piece is new, and that piece is coming from, well, the combination of the A and the B, which just gives that. So that is, of course, a remarkable result. It's a remarkable result because we started out with a set of equations, well, there were 4 of them, right, which looked pretty complicated, and it looked like you could get all sorts of different terms. But if you do look at the conservation of energy equation, just written in terms of the coordinate, derivative of the coordinate r with respect to the proper time, then you can just write down a simple effective potential for it. And the remarkable result is that there is just one extra term. In this equation, right, in that equation, or this equation, or the one on top that I just erased, there is just one extra term. And that extra term is the relativistic correction. Right? And it is exact, right? It is exact because we have not made any approximations, right? The Schwarzschild solution was obtained exactly, right? That's the function A and B. The equation for free fall, right? The angle of Newton's equations. Again, we don't need to do any approximation. You might think that at some point you have to use that the field is weak, but you don't, right? You don't. You just plug them in, you use the A and B, and what you do find is that the equations are almost exactly like the Newtonian equation. Well, of course, here's as a proper time, right? So there's a little bit of a difference. But if we ignore this little aspect of having the proper time here, the potential is just changed by just one term, right? And the new term is this j squared term. And so that's quite remarkable. What else is remarkable about this result? Well, what else is remarkable is, of course, nothing happens on the Schwarzschild radius, right? So if you look at this, there's no 1 minus 2mg over r terms in it, right? This seems to be completely well behaved. There's only one extra correction. And so that extra correction is the one that is responsible for the precession of perihelion of Mercury. Right? So this term here is responsible for the precession of the perihelion of Mercury. Right? It is responsible for the precession of the perihelion of Mercury, which means that you can actually work that out rather quickly, right? And I mean, it is my choice not to go into too many details about the characteristics of the orbits, but nevertheless, you can look up, for example, in Landau-Lifshitz, right? If you look at the first volume of classical mechanics, in Landau-Lifshitz, it says, it's actually, as it often happens in Landau-Lifshitz, that some very interesting and difficult problems are assigned just as a problem in the book and not worked out explicitly, right? But one of the problems is if I give you that there is a correction to the potential, which is some constant, right, which Landau-Lifshitz maybe writes as beta divided by r to the n, right? If you have a correction to the potential, dv, which is of this form, where beta is some number and it involves some power, right? Work out what the precession planet's orbit is with this potential, and he gives the answer. It's in Landauerisch. It's a classical mechanics exercise. And so basically we can take that over. We can take that over because that, of course, was well known already at the time of Einstein, and what, these various celestial mechanics perturbation, what kind of effects they would have. And so we can say that at this point, a number of consequences of the general theory can be worked out in a rather straightforward way by noticing that one main effect is to add an extra term to the equations of motion for a point particle, which has that shape. It goes like 1/r cubed, right? And it depends on the angular momentum as well, right? You see, it does have a j square there. And incidentally, it is a relativistic correction, because if you were to put the speed of light in it, then it would appear there would be a c squared in the denominator, right? So it is a genuine relativistic correction, and so you can then work out what it is. So I think we're running almost out of time, and so we are going to continue on this next time. I think there is a very nice discussion of what happens to orbits in Jim Hartle's book. So if you really want to read a little bit more, I mean, we don't have a lot of time here in this class to do that, but he has a very detailed discussion of what kind of effects you have in drawing, shapes of potentials. Now, there is one thing which I haven't mentioned yet, which is kind of interesting about that result, this correction, right? And that is the negative sign, because if you do plot what this potential looks like, right? Right, then so if you plot V effective of R, right? Then of course at large R, this relativistic correction is irrelevant, right? So at large R, you just have the 1/r. Just have the 1/r part. Then as you get to smaller r, you have the centrifugal barrier term, which picks up, right? The 1/r squared correction, which is positive, right? So the potential now goes up like this, right? But then when you get to sufficiently small r, then the 1/r cubed, which is dominant for small r, it goes negative. So the potential then looks like this, right? And so you can work out what these turning points look like, right? And so you can find that this R max here is equal to j squared divided by 2mg times 1 minus the square root of 1 minus 12 m squared g squared divided by j squared, for example, right? And this R min here, again, as a function, of course, of the angular momentum, right, of the j squared, and the mass of the body that is at the origin, right? And so this R min is equal to j squared divided by 2mg times 1 plus the square root of 1 minus 12 m squared g squared divided by j squared. Right? So you can see that the physics of what happens when you have a point particle or a planet that sits at a certain distance from the point source, from the sun, if you wish. That, of course, depends on where it starts out, right? So if it starts out on this side, then, of course, you have a stable orbit and there is no problem. But if the radius is too small, then you have an unboundedness corresponding to the 1/r cubed, right? And so anyhow, I think we'll discuss this a little bit more next time. As I said, we don't have the time to go into too much detail. I think one of the interesting limits is, of course, what happens to a photon. Right? What happens to a particle that is exactly massless And in that case, the treatment is slightly different because for a photon, we have that d tau square is equal to 0. So photon orbits, right, correspond to d tau is equal to 0. Right? So in that case, you have to do a separate treatment. Everything that we've done so far applies to a particle that has a finite mass m, right? And in the case of a photon, of course, there is no stable orbit. Right? So a photon cannot orbit around in the solar system. Right? A photon will just eventually escape to infinity. So the shape of this curve that I've drawn there for the effective potential applies to a particle that has a finite mass, but of course it works perfectly if you have something like a planet. So the plan next time is to continue a little bit on this. Right? I think I should mention at least at this point that this predicts for the precession of perihelion Mercury, a precession which is 42 arc seconds. Well, it's not the sign here, per century. Per century. So in other words, if this is the sun, right, then the orbit of Mercury, if there was no 1 over r cubed correction, then that would be just a Kepler ellipse, right? It would be like that. But because of the 1 over r cubed term, the orbit looks like a rosetta, right? It looks like that. And so the precession of perihelion Mercury has to do with the movement of this axis, right? And that axis, right, which is aligned with the direction of the ellipse, right? So that axis moves by 42 arc seconds per century. It's a very small movement, but nevertheless it is there. And that is completely explained by this correction. So the relativistic correction gives 42, which was the number that had been measured and known before. And so I think next time we'll talk about some other things that come out of this orbit discussion, which is, for example, what happens to light. As I mentioned, for photons, you have to do a slightly different treatment. And then you find that photons are also, well, they don't orbit, right? But they do get deflected by the sun, and the amount by which they get deflected is important to know because it is another test of general relativity in somewhat different domain, right? Because you're dealing with an ultra-relativistic particle in that case. So anyhow, that's what we're going to talk about next time is a little bit more stuff that relates to the solution of the problem of equations of motion for the Schwarzschild metric, and then after that we'll do some other things. Yes, you had a question? No. So any questions or comments? Yes?
Did Einstein make this prediction, or did Schwarzschild?
Einstein did.
Okay.
Einstein already calculated the 42 arc seconds per century before even he had the complete theory written down, because I guess you realize that probably the weak field limit is okay, and that you can get the answer by doing some approximations. So he got that even when I believe his equations were just r mu nu is equal to minus 8 pi gt mu nu, which was around 1915. I mean, we're talking just about a few months before he wrote down the final form of the theory. He understood early on that there's going to be an effect, and that the effect would be right on to compared to what people had known for a rather long time, because celestial mechanics, of course, had started as becoming a major discipline at the beginning of the 19th century with Laplace, and people had calculated accurately, all sorts of perturbations on the motion of planets, and had sorted out what kind of effects you would get. And then as these calculations became more and more sophisticated through the 19th century, people realized that at some point some things just didn't quite work out. And the precession of the perihelion of Mercury, I believe, was the only case, because everything else seemed to fit perfectly. The motion of the moon, the perturbations due to Jupiter, right, all that stuff seemed to fall in place very nicely, but there was this anomaly that had to do with Mercury, and that remained unexplained. People couldn't quite figure out what it was, right? Maybe it was this oblateness, the fact that the sun was not spherical. Maybe it was something else, some mysterious deviation in gravity at short distances. So when Einstein calculated the precession of the perihelion of Mercury, he got 42 arc seconds right away, and so that was quite remarkable. I mean, and it is remarkable also the fact that after the dust settles, that the equations are not that bad, right? I mean, it's you can even calculate, of course, exactly the Schwarzschild solution. He had done it in the weak field limit, but you can get to an answer in the end rather quickly, because you start at some point to understand that all it comes down to is just a small correction to the Newtonian potential, to the classical Newtonian potential for a body like the sun, which is of that shape, of that form, right? And that is enough to give you the 42 arc seconds. This is what will give you that correction. So it is kind of nice. And I think we appreciate that, particularly today, in view of the complexity of this theory, right? In view of the fact that this theory is really phenomenally complicated when you look at it, the original field equations, right? With all these things that appear in it, determinants of the metric and inverses and fine connection, right? So that you can sort this out in certain, in certain situations rather quickly is remarkable, right? And
so other planets also have all the planets also have this relativistic.
Yes.
But just too small.
All the planets have it, right? But of course, what you need in order to have a large correction is that, well, the mass is large. Of course, that's fixed. That's the mass of the sun. So the only thing you can play with is a large angular momentum and a small radius, right? And because it goes like 1/r cubed, of course, it will die out very quickly as a function of the distance, which means that already for Venus, this effect is very tiny. And in fact, I can't remember what the number is supposed to be, if it ever been measured. Probably measured today, but yeah. So, but at that time, I think in the case of Mercury is very close to the sun, right? And so this effect is, if we are lucky enough, right, that we have a planet that is close enough to the sun, so that this effect is actually readily detectable. And if it had not been detected, then it would have been a prediction that Einstein would have made that had to be verified. And of course, that is what happened with the deflection of light by the sun, because deflection of light by the sun is something that nobody had thought before, right? I mean, maybe Laplace did, because Laplace thought, that light was photons, and probably, they might get bent by a massive object. But Einstein was the first one that actually told you exactly by how many degrees you would get this deflection.
Did he use a weak field metric, or did he use a Schwarzschild metric?
Oh, I'm sure he used originally the weak field metric, right? Because the Schwarzschild solution came out only in 1916, after he had written down the equations, right? So Schwarzschild was in Berlin, right, at the time. He was not a young kid. I mean, he already had been, doing physics for a number of years. And Einstein was in Berlin. Schwarzschild was in Berlin as well. They talked to each other. Presumably, Einstein gave talks at the Prussian Academy of Science or wherever. And then what happens was, of course, it was the middle of the war, so Schwarzschild got sent to the Russian front, right, and to fight World War I, 1916. And now, of course, you can imagine, when you have a Russian winter on the Russian front, what do? You look for static isotropic solutions of the field equations, right? Because when you have temperatures, sub-zero for months, where the wind is blowing and snows every day, then that's there's not a whole lot of fighting going on in the trenches in the middle of the winter. So he found this solution right away, and it's a matter of patience, as you saw, just working out all those derivatives and making sure you don't do any algebra mistake along the way. So Einstein, of course, was elated that such an exact solution could be found, because Einstein was probably one of the first to realize that finding exact solutions was going to be a real challenge to these equations, because the nature was so complicated. In fact, the solution that is related to it, which is the rotating black hole Kerr solution, that was found in 1961. So it took a long time to do just the next case, right, where this mass is not fixed, right, but it has an angular momentum that already is a lot harder, a lot more algebra involved in doing that. So anyhow, I'll see you next week then.